Hello everyone. Let me start by giving a brief overview of our project Boston Bus Equity. This project analyzes equity and reliability in MBTA bus service by combining three main datasets: ridership, arrival departure records, and passenger surveys to understand how delays are distributed across Boston and how they relate to neighborhood demographics, especially race. Rather than building a full operational dashboard, the focus is on punctuality, delay patterns, headways, and on time performance to reveal where and for whom the delays are most severe. In the earlier stage of the project, we tried to link lateness with neighborhood racial characteristics but found no meaningful patterns because the demographic data we used was sparse and inconsistent. So, to address this, we replaced it with US Census Bureau's uh, ACS 5-year estimates and integrated them with MBTA GTFS data and tracked shapefiles, allowing every stop to be accurately aligned with high quality demographic information. Using this improved dataset, we analyzed the problem from three angles. First, unsupervised clustering helped identify whether stops serving similar racial compositions tended to fall into similar lateness groups. Second, supervised learning with XGBoost revealed whether features more strongly influenced lateness predictions and whether race-related variables contributed. Finally, targeted statistical and spatial analysis allowed us to compare delays across the routes, stops, and demographic categories. To support these methods, we performed intensive data cleaning, like converting demographic fields to numeric, conducting spatial joins, merging stop time data with standardized route IDs, removing invalid entries, optimizing indexing, and constructing route level features such as headways, boardings, earliness, and on time performance. For visualization, we created plots and maps to show racial and ethnic distributions across Boston census tracts, revealing clear spatial patterns. Additional performance plots such as delays, trends in lateness, overtime, and comparisons of consistently late routes provided a system level picture of reliability and highlighted where service struggles the most.
In this section of the project, our goal was to understand what drives bus lateness and whether any of these patterns show signs of unintended bias. We approach this using a combination of XGBoost, predictive modeling, and sharp explainability tools. First, we engineered a set of features that capture different aspects of the transit system. These included operational variables like schedule headway and time point order, and temporal factors like time of the day, peak versus off-peak time, and also demographic characteristics like racial composition around each stop or route. After training the XGBoost model, we achieved a solid predictive performance, explaining roughly half of the variability in lateness, which is kind of expected for a system with many external influences like weather and traffic. Next, we used sharp values to interpret the model. The global feature importance plot showed that time point order and schedule headway are the strongest drivers of lateness. So this means that delays naturally accumulate as bus progresses along a route, and longer gaps between buses make delays more likely. Interestingly, some demographic variables also appeared as meaningful predictors. This doesn't automatically imply bias, rather, it signals that demographic context may correlate with other unmeasured operational features, such as road conditions or demand patterns. To go deeper, we performed counterfactual fairness tests. Here, we held all features constant for a typical stop and varied one demographic variable from 0 to 1. The idea is if the only thing we change is the racial composition, does the predicted lateness change in a concerning way? What we found out is the effect sizes were generally small, usually less than half of a minute, and often non-monotonic. For example, percentage white showed a downward trend at low values and then flattened, while a percentage Asian and black sometimes increased predictions in mid-range values. These patterns suggest complex interactions rather than a direct systematic bias. Overall, the key takeaway is that the model's predictions are primarily driven by operational and structural factors, and while demographic variables do have some influence, the counterfactual tests indicate that their effect is modest and context dependent, and not strongly directional. This gives a good foundation for model refinement and helps us identify where fairness constraints or additional operational data might improve equity and performance.
We now focus on equity and lateness. When we map lateness onto the city and combine it with the census race data, we consistently see that the routes running through neighborhoods with high share of non-white residents experiences higher average lateness and are not reliable. This is the visualization of MBTA bus stops all over Boston. And this is the distribution of whites and blacks at the MBTA bus stops. This is the scatter plot of race versus headways versus riderships. And here we have visualized the lateness versus the race. Here we specifically took 4 race: white, black, Asian, and Hispanic. Here we have the confusion matrix between democratics and lateness. We have visualized lateness using box plots for the 4 specific race. Route lateness versus the higher population that are available in that particular area. Route lateness majority of white versus non-white areas. Here we did k-means clustering for route lateness versus non-white population areas. Here we have visualized the democratics and bus routes. This tracks the democratics and the bus stops that has more delays, average lateness. Here we have visualized the correlation between democratics versus lateness. As you see, the areas that has major white population are negatively correlated with lateness and seems to be more reliable. This is the final visualization and the final result of this project.